Hi, welcome to Chem 103 Lab. For your first experiment, you're going to be investigating how to measure mass and volume of different objects, and then use those numbers to figure out a density of a certain object that you're measuring, and from its density be able to determine the identity of an object. When you're finished with that task, you'll be able to compare the density that you measured from and calculated from your measurements with the true value that's reported in a table and see how close or far you were able to get. And by that I mean assess the error that you made. So when we're thinking about error, what we're thinking about is deviations from the true value. So these are things that are related to um, the accuracy or precision of your instrumentation, how many times you performed a measurement or a calculation. These are things that contribute to maybe not getting exactly what was reported in a certain table. So when we're thinking about error, what we're thinking about is kind of the difference between the measured and the true value. And notice that these have absolute value marks here, because error is always positive. So when we're reporting out our error, we're going to be getting positive values. Because really, we're not thinking about so much whether the difference is high or low. Really, what we're thinking about is how different are the values. A really useful way to communicate about our error is the percent error. So that's where you take the measured value, so from your measurements, and compare it to a true value. So the true value is often found in a table of data, and in experiment 1, this table is given to you. So this is given in the experiment. Generally, if we ask you to calculate the error, we will give you information about what the true value is. So one of the challenges when we're working with calculating a percent error and thinking about how different our measured values are from the true values is not so much in using this equation, because it's fairly straightforward, but really it's with thinking about the significant figures associated with it. So when we have a measured value, we might have fewer or more significant figures than we have of our true value. And we know that when we do subtraction as our first step, what will happen is we may gain or lose some significant figures. Now, because we're subtracting, we'll most likely lose some significant figures. So we're going to follow our subtraction rules first when we're thinking about significant figures with error. And this is where we think about decimal places. And then we're going to focus on our division rules for significant figures, and that's when we follow whichever one has fewer significant figures. So let's do an example to get you thinking about this. So let's say that you're in lab and you measure a block to have a density of 8.445 grams per centimeter cubed. The value found in the table, meaning the true value, is given here as 8.43 grams per centimeter cubed. So we want to find the error using correct significant figures. So the first thing we're going to do is figure out the measured minus the true value. And the reason that I write it this way is because I'll be able to line up my decimal places and have a better understanding for how many significant figures I should actually report for this calculation. So I'm going to take 8.445 and subtract 8.43. When I do this subtraction, I will get 0.015 as the difference. Now again, I'm following the subtraction rules, so what I'm going to do is line up my decimal places and see that there are only 2 decimal places that we have in common. And since these leading values are zeros, these don't count, and we only have one significant figure when we do our subtraction. That means that our percent error cannot have more than one significant figure. So now to find the percent error, I'm going to take the measured minus the true value right here, and I'm going to write down the entire value because we don't round until the very end, and I'm going to underline the 1 just so that I remember there's only one significant figure. Divide by the true and multiply by 100% to get a percent error. When I do this calculation, I'll get 0.2%. And again, notice that's just one significant figure. Generally, the closer your measured and true values are, the fewer significant figures you'll have in your percent error. So generally, percent error doesn't have more than 1 or 2 significant figures. Unless you're really off, that you'll have maybe 3, but generally it's 1 or 2 as a good rule of thumb. Another way that we can think about error is error that's directly related to our measuring device, and that's called uncertainty or relative error. And this describes the error within a numerical value due to the measuring device. So depending on what you are measuring and what you are measuring with, you will have variations in your relative error. So varies by device or tool or instrumentation. It really all depends on what you're using. And uncertainty or relative error is always reported as a plus or minus value. So that means that the actual value can be a little bit less or a little bit more than what you actually saw on the measuring device. Here's an example. So if you've ever used a pipette, right on the pipette, it'll say something like 0.05 plus or minus 0.05. We know that the balances in our laboratory have an uncertainty of 0.001 grams, meaning the mass can be 0.001 gram less or more than what we see on the balance. So when we're thinking about a relative error, really a relative error is an uncertainty with respect to the measurement we took. So we report the relative error as the uncertainty value. So that's our plus or minus value over the measured value times 100%. So let's do a quick example. So for example, let's say that we measured the mass of an object to be 1.50 grams plus or minus 0.001 grams, and we want to know the relative error in the measurement. So the relative error is going to be the uncertainty, the 0.001, divided by the measured value times 100%. And notice that the uncertainty only has one significant figure, so we'll only report 1 in our relative error. So we get 0.08%. And notice how small that is relative to the measurement that we took. So we know that the data we took from that balance is pretty accurate, pretty precise. Okay, so then we want to think about now the individual measurements that we're taking in this experiment. So in this experiment, we're thinking about the mass, we're thinking about the volume. Those are measurements that we'll be taking, and we'll be using those measurements to understand the density. So to calculate the density and then use the density to identify our objects. So what is mass? Mass is the amount of matter in a given object, and we will be using our balances to understand this and measure it. So when you're using the balances, we always want to press the 0 button and make sure the balance actually reads 0 before we take any measurements, because otherwise it could really throw off our results. If you're measuring something that's easy to put on a balance, like a block or a cylinder, or just some object, you can go ahead and place it right on the balance and read what it says. If you have a liquid or a powder, or you just need to place the substance you're measuring inside of something so it doesn't go everywhere, then we always first obtain the mass of the container, then put the sample in the container and obtain the mass. So the mass of our sample will then of course be equal to the mass of our container plus the sample minus just the mass of the container. And something that is sometimes challenging to understand is when you're using a balance, you don't want to apply significant figure rules to it. You just want to record all the digits from the balance screen. So do not attempt to round, just write down all the numbers that you are given. So that's mass. The next thing we'll be talking about is volume. So there are two ways that we're going to be measuring or calculating volume in this experiment. So one way to directly measure the volume of something is to use the water displacement method. With the water displacement method, we're going to be measuring irregular solids. So in this case, it will be the metal shot. The other way to measure a volume is to measure the dimensions. So this is referred to as linear measurements. So measure the dimensions. And so you can do this when you have a regular object such as a block or a cylinder. So there are several of these within experiment 1. To do this, we will use calipers. And the calipers that we have measure the dimensions pretty well, pretty precisely, but they measure in millimeters, and we want centimeters. So to go from millimeters to centimeters, all we have to do is divide by 10, as you'll hear in the video. So once you have all your dimensions, then you can apply some equations to solve for the volume. So if you have a block, you're going to do length times width times height. For the cylinder, you're going to do pi r squared times the height, where r is the radius. Or if you have a sphere, you'll do 4/3 pi r cubed. Once you have the mass and the volume of whatever you're measuring, then you can solve for the density. So the density will be a calculation, not a measurement. And the density is a ratio of the mass over the volume. So D is mass over volume. So in lab, for the mass, your units will always be grams, but your volume, depending on which method you have, could have different units. So if you're doing water displacement, then your volume would have units of milliliters. If you're using linear measurements, then your volume will have units of centimeter cubed, but those are equivalent units. So because density is independent of how much sample we have, we can use this property to identify our samples. Once you identify your sample, you'll be able to know how well you measured it based on the percent error that you